The magnetic field produced at any field point P by the current in a conductor is the vector sum of the fields due to all the moving charges in the conductor. This statement is the principle of superposition. We can think of the conductor as divided into short segments of length dl. A typical segment is shown here. We can use the relations we've just gone over to find the magnetic field caused by the current in this segment. The volume of the segment is A dl, where A is the cross-sectional area. Suppose we have n charges q per unit volume, then the total moving charge dq in the segment is dq equals nq, the area A, times dl. So you can see that that will give a total charge in this segment, because n is the number of charge carriers per unit volume, put it that way, and each material has its own value of charge density. Q is the charge, and A is the area of this element here, and dl is the length, so that will give us the total charge. The moving charges are therefore equivalent to a single charge dq, travelling with a velocity equal to the drift velocity v. Fields due to random velocities of the carriers will on average cancel out at every point, so dB becomes u0 over 4 pi. We're going to insert the dq here now, and we get v sine theta over r squared. We're just going to insert all of this. So if we insert all of this dq and just expand it out, we get u0 over 4 pi nqva dl sine theta r over r squared. We know that nqva, so that basically if you just expand all the SI units out, you'll find that is basically the current. That being so, we can rewrite this as dB equals u0 over 4 pi. The current I now, we replace that with I, dl sine theta r squared. So where dl is a vector of length dl in the same direction as the current in the conductor, and r is a unit vector in the direction from the current element to point P, as shown in the diagram here. The field vectors dB are exactly like those set up by a positive charge dq moving in the direction of the drift velocity v. These two equations will come up often in questions, and this is known as the law of Biot and Savart. To find the total magnetic field B at any point in space due to the current in a complete circuit, we have to integrate one of these expressions symbolically. So we have to do this basically. We will learn how to do this in specific cases in the next several sections. We must point out that it's impossible to verify this equation directly, because we can never experiment with an isolated segment of current carrying circuit. The only thing we can measure experimentally is the total magnetic field B for a complete circuit. But we can still verify this equation indirectly by calculating the magnetic field B for various current configurations and comparing the results with experimental measurements. If matter is present in the space around a conductor, the field at any field point P in its vicinity will have an additional contribution resulting from the magnetization of the material. We'll return to this point later. Unless the material is iron or some other ferromagnetic material, however, the additional field is so small that it's usually negligible.